Hello everyone, welcome to Dr. Ravi's Academy. From this video lecture, you will be understanding the polar velocity diagram of a hook joint. The hook joint is also known as universal coupling. Here, so this particular representation also known as variation of the speed of the driven shaft with respect to driving shaft. To understand this polar velocity diagram, that means the variation of the driven shaft angular velocity with respect to driving shaft angular velocity is a polar velocity diagram. So that you are going to understand the salient points, salient features of the polar velocity diagram. For that purpose, let us consider the expression for the velocity ratio. Omega 2 divided by omega 1 is equals to cos alpha divided by 1 minus sin square alpha into cos square theta, where alpha is the angular misalignment between the driving shaft and driven shaft, where theta is the angular displacement which is a variable, and omega 2 is driven velocity, driven angular velocity, and omega 1 is driver angular velocity which is a constant. So because it's a constant, you can write down omega 2 is equals to it is omega 1 cos alpha divided by it's a 1 minus sin square alpha into cos square theta. So you are representing angular velocity. You can understand from this equation there is a continuous variation of the angular speed of angular velocity of the driven shaft with respect to driving shaft. Now let us calculate the various values of angular velocity of the driven shaft. Here for maximum value of omega 2, maximum value of omega 2. Here let us look at this. This totally is a constant, and sin square alpha is also constant. When omega 2 is maximum, here because it is 1 minus cos square theta, this variable also if it is maximum, so that your omega 2 becomes maximum. So cos theta maximum value is 1, and if you substitute cos square theta as 1, your equation becomes it is omega 2 is equals to omega 1 cos alpha divided by it is 1 minus sin square alpha. Your cos square theta is maximum value is 1. So it is you can write down this as omega 1 into cos alpha divided by this becomes cos square alpha and cos square, and your omega 2 max is omega 1 divided by cos alpha. So this is equation 1. And let us calculate the minimum value of omega 2. For minimum value of omega 2, the condition is your cos theta value becomes the minimum value of this is 0. So the moment it is 0, you have straight away omega 2 minimum, you can write down is it is omega 1 times it is cos alpha. This is your equation 2. You got that maximum and minimum values of the angular velocity of the driven shaft. Now let us calculate equal velocities. When you have both a driver as well as driven angular velocities are equal, here that means this is equals to 1, and your cos alpha for equal velocities for omega 2 is equals to omega 1. So when these two are equal, it is cos alpha is equals to it becomes 1 minus sin square alpha into cos square theta. So let us simplify this. Let us bring this this becomes a positive sin square alpha into cos square theta. You can write down it is 1 minus cos alpha, and cos square theta is equals to 1 minus cos alpha divided by sin square alpha. You can write down it as 1 minus cos square alpha, and this 1 minus cos square alpha you can make it as cos square theta is equals to 1 minus cos alpha divided by 1 minus cos alpha into 1 plus cos alpha, you can write down, and these two gets cancelled, and you have cos square theta is equals to, it is 1 by 1 plus cos alpha, and secant square reciprocal of this is secant square theta is equals to 1 plus cos alpha, and you can write down, it is secant square theta minus 1 is equals to cos alpha, and as you know that secant square theta minus 1 is tan square theta, and your tan theta is equals to under root cos alpha, cos alpha. So this is the value of the theta at which you have the angular velocities are equal. Now you got all the salient points. This is equation 3 you can call. It is for maximum, for minimum, and for equal. Representing all these values on a diagram is called polar velocity diagram. So let us draw the circle for the angular velocity of the driving shaft, which is constant. I am representing in the form of a circle because it is the radius remains constant. This is my angular velocity of the driving shaft omega 1. But whereas if you look at that, the angular velocity of the driven shaft continuously varies with respect to this. So that means it becomes a minimum at one point and a maximum at other point. So that can be in the form of ellipse. It is in the form of ellipse. You have this maximum value is how much you got from equation 1? It is omega 1 divided by cos alpha is your omega 2 max. This is your omega 2 max, and here minor axis will be omega 2 minimum. So it is omega 2 minimum will be, it is omega 1 times it is cos alpha, and you can identify equal velocities. I am representing with a small e, where you have omega 1 is equals to omega 2, both are equal, and the condition as you got from equation, it is tan theta is equals to under root cos alpha. So this is what exactly known as the polar velocity diagram. Representing the salient points or the variation of the velocity of the driven shaft with respect to the driving shaft is called polar velocity diagram. Thank you.